If you major in computer science, almost certainly in your first year you'll take a course called something like Intro to Data Structures and Algorithms, which is a course covering the basic collection types most commonly used in code, and the various algorithms associated with those collections, primarily searching and sorting algorithms. The course also tends to serve as the student's introduction to the formal analysis of algorithms, that is, the student's real introduction to proper computer science. In this unit, we're just going to look at data structures, and we'll follow up with searching and sorting algorithms in another unit. When we talk about data types, we can make a distinction between primitive types and composite types. Primitive types are atomistic pieces of data, like individual numbers or strings or booleans. A composite type, in contrast, is a bundling of these elements together in a contiguous fashion, meaning that they're all placed next to each other in memory. Composite types come in the form of either an array, that is, a sequence of homogeneous elements one after the other next to each other in memory, or in the form of what's sometimes called a record, or more commonly just an object, that is, a bundling of heterogeneous items. Like, say, a record representing a person may start with a string, which is the person's name, followed by a number, which is their age, followed possibly by other pieces, like, say, their address or their nationality, etc. Very importantly, though, these various things which make up that person, if this is truly just a record, they are placed contiguously in memory, one after the other. For efficiency reasons, you might have padding in between the elements, but aside from that, all the pieces are contiguous. Now, composite types may be considered to be what we call a data structure, but the term data structure is more broad, as a single data structure also may encompass a group of composite types which are associated together by references connecting them. Like, say, in one array or one record, you'll have a reference, a pointer, pointing to some other array or record. Effectively, we're talking about data which is related, but not necessarily grouped contiguously in memory. Aside from arrays and records, perhaps the simplest data structure is what's called a node. A node is a record with two elements, a value and a reference which may point to another node. So, for example, here we have two nodes with the reference of the one on the left pointing to the starting address of the other node in memory. The point of a node is to represent a value, but potentially associate that value with some other value as pointed to by the reference. As we'll see, nodes are the building blocks for larger data structures, such as the linked list, or in some cases, graphs and trees. First, considering just a node though, how would we represent this in code? Well, in Python, we would create a class, and we'd call it node, obviously. We'll have our node class simply inherit from the object class, which, remember, is the generic type at the top of Python's type hierarchy. And in our constructor method, recall that in Python the object itself is passed to the first parameter of a method, so by convention we call it self, and we'll give our constructor two other parameters, item and an optional parameter, other, which by default will have the value none. So when we create a node object but we don't provide an argument for the other parameter, by default it will have the value none. In the body of the constructor, we simply give the node object two attributes, item and other, and we assign to them the values passed to the item parameter and the other parameter. The item attribute is the value of the node, the item represented by this node, whereas other is a reference pointing to some other node. By default, though, it's none, so by default we have a node which doesn't point to any other node. As for the other methods of our class, the things we want to do with our node is retrieve the item, retrieve the value with getItem, also retrieve the node pointed to by this node with getOther, change the value of the node with setItem, or lastly, change which other node is pointed to by this node with the setOther method. So a getter and setter for the value of the node, and a getter and a setter for the reference to another node. As we've already established, an array is a sequence of elements which are all stored contiguously, and importantly, those elements are all of the same type, they're homogeneous, or failing that, they're all at least the same size. And in fact, the array itself is of a fixed size. Once it's created, it doesn't shrink or grow. A list, in contrast, is a variable-sized sequence of elements. The number of elements can actually change through the lifetime of the list. Likewise, the elements of the list need not be all of the same type and size. They can be heterogeneous. The two most common ways to implement a list are what's called a linked list, which is a list composed of nodes, or an array list, where the list is made up of one or more arrays. In a linked list, each element is represented by a node, with the first node designated as the head of the list and the last node designated as the tail. The advantage of the linked structure is that it makes it easy to add and remove elements from the middle of the list. Like, for example, here, given this list of 3 elements, if we want to insert an item such that it takes the place of the second position and shifts everything after it one spot over, we can do so by simply creating that node and updating 2 references, the reference of the node that precedes where we're inserting this new node, and the reference of the node which we are inserting itself. This works because, unlike in an array, the elements of this sequence need not be stored contiguously. Each node is allocated separately and given its own spot in memory, wherever that may be, and the logical sequence of the list is formed simply by the chain of references. The elements all belong to a logical order of the list, but their actual storage in memory might be in any order. But as long as we keep track of where the head is located, we can get to any of the elements. We can follow the chain from one node to the other, all the way to the tail. The end of the list is simply denoted by a tail node, a node in which the reference is null. It's the one node that doesn't point to another node. So now, consider how we might implement a linked list as a Python class. In this case, though, we'll keep things simple and not include any operations for removing or inserting items in the middle of the list, but rather just include operations for retrieving values of items in the list, changing the value of an existing node in the list, and appending an additional item to the list, tacking on a new node. So first off, we will call this class linked list, and we will have it inherit directly from the object type. And in the constructor, we do nothing but simply give our linked list object an attribute head, which will be our reference to the head node, but we'll keep things simple here and say that when you create a new linked list, it always starts empty with no nodes whatsoever. So in the constructor, we simply assign self.head none. For our append method, the argument is item, the value to store in the new node, and then we create from that a new node. What we do with this new node depends on whether or not there already is a head or not. If there isn't already a head, then the condition if self.head will test false, because self.head will be equal to none, and none is considered a false value in Python. So the else clause will execute, and we will simply assign the new node to self.head. And now we have a list with one node, with one element. On the other hand, if self.head is not equal to none, if there already is a head, then what we need to do is find the tail node. And we do so simply by following the chain of references from the head node to the last node in our list, which is the node where the reference is equal to none. And see here, we can do this by assigning self.head to a variable node, and then we loop with a condition of node.getOther. As long as node.getOther returns a node which will test true rather than none which will test false, then the loop keeps executing and we keep assigning the next node to the variable node. Once the loop exits because we've hit the tail node, then we invoke node.setOther with the new node. So now what was formerly the tail node is pointing to this new node, and the new node which we created is the new tail node. As for our getItem methods, it simply has one parameter, idx, short for index, which is the 0-based numeric index of the item we want. So say if index is the value 4, then we loop to the 4th item in the list, the 4th node, and then retrieve that value from that node with node.getItem, and that's the value we return. Notice that in our code here we're using the for-in loop in Python, and we're using the built-in range function, which returns a sequence of numbers up to the argument specified. So if index here is 4, range will return a sequence of 0, 1, 2, and 3, not including 4. That's the tricky thing to remember about range, is that it's not inclusive. So we get a sequence of 4 numbers, but starting from 0, so not including 4 itself. In this case here, the elements of the sequence which we are iterating over in this for-in loop doesn't really matter. All that matters here is the number of items that we are iterating over, because the variable I here is not actually getting used. Also note in this code that if we were to specify an index that exceeded the bounds of the list, like say if our list only had 5 nodes in it, and we specified an index of 10, well, that will end up triggering an exception, because in the 5th iteration of the list, we're going to end up assigning none to node. And then in the next iteration, in the 6th iteration, if we invoke node.getOther when node is none, then that's an error. You can't call a method on a none object, obviously. So we get an exception, which really is the behavior you want. If you specify an index out of bounds, you should get an exception. Lastly, notice that the setItem method looks really just the same, except we're specifying an item parameter, and then in the last line we're not returning a value, we're just calling node.setItem and passing in the item. We use the same loop to find the node at a certain index, it's just we then use setItem instead of getItem once we find the node. Now, it may have occurred to you that getting and setting items in a linked list seems kind of inefficient because it requires traversing the entire list up to the certain index we're trying to get or set. Mostly for this reason, a linked list isn't always the most desirable form of a list. If what you mostly do with a list is iterate it through it sequentially, then a linked list can work out really well because you're just going from one item to the next. If, however, you need so-called random access to the elements in your list, that is, you tend to jump around a lot from different places in the list, then probably a better solution is what's called an array list. As the name implies, an array list is a list stored in the form of an array. If at any point our list exceeds the length of the current array, what we do is create a new larger array and copy over all the existing values. Now, of course, copying all the existing values into a new array gets expensive, especially as our list gets larger. So to avoid having to do this operation too often, a common strategy is to double the size of the array when we resize the array. For the most common usage patterns with lists, this doubling behavior tends to minimize the number of times the array ends up getting resized. In some scenarios, you may find it useful for your array lists to actually also shrink when enough items are removed from the list. Doing this can help keep down the memory usage of your program, but as long as you're not terribly concerned with your memory usage, it's not strictly necessary. If the array of your array list has 1,000,000 slots, but you're only using a few of those slots, sure, that's wasteful, but the list will work perfectly fine. The opposite, of course, cannot be said. At any moment in time, the array has to be large enough to at least hold all of the current items in the list. So, here's our quick and dirty Arraylist class in Python. First note that the constructor takes no arguments because our array lists will always start off empty. The array, however, will start off with a size of 10. So note that the class distinguishes between the length of the list and the length of the array. They are not the same. The array will always be at least as large as the list, but it of course may be larger, and that's how things start out. The list has 0 items, but the array has 10 slots. Just a reminder here, looking at the second line, we're creating a list with one item, the value none, and then we are multiplying that list times init size, which is 10. And recall in Python, when you multiply a list times a number, what you get is a new list with the items of the list repeated that number of times. In other words, we're taking our list and we're concatenating that list with itself 10 times over. So we end up with a list with 10 items, all of them with the value none. And that's the list we assign to self.array, the array attribute of the ArrayList object. Note that it doesn't really matter what value is in the slots of the array which are not yet part of the list. Those slot indexes which are past the list length, which at the start are all of the indexes. I just chose the value none because, well, something has to be there. Now looking at the append method, which takes an item and tacks that on as an additional item at the end of the list. So we're expanding the size of the list by 1. First off, if the current length of the list is equal to the size of the array, then that means there are no more slots to use and we need to expand the array. So we double the size of the array by taking the existing array and concatenating to it a list of none values which is equal in length to the current array length. So again, just be clear about the Python code. First, the list with a single value none is multiplied times the current array length, giving us a list of none values that is array length long, and then the plus equals operator is taking the current value of self.array, adding it, concatenating it to the list of none values, and then lastly assigning that new list to the attribute array of the object of self. Recall that the plus equals sign operator is just a convenience that spares us from having to write, in this case, self.array twice, both on the left side of the equal sign and on the right side. X plus equal y adds x and y together and assigns the result to x. So now we've doubled the actual size of the array, and so we need to update the array length attribute and double it as well, which we do so by simply multiplying it by 2. So now we can be assured that the array is long enough to append this new item, and we append the item by simply assigning to the index of the current list length. And having added the item, we now increment list length because the list is now 1 larger. As for the getItem and setItem methods, again their logic is very similar, but note in both we first have to make sure that the specified index is in the range of our list. We don't want our list to erroneously get or set values in parts of the array which are beyond the end of the current size of the list. So if the specified index is greater than or equal to the current list length, then we will throw an exception saying that the index is out of bounds. If the index is in bounds of the list, then we simply return the value at the specified index within the array, or we set the value at that index in the array. Lastly, I should note that for demonstration purposes, we are ignoring the fact that the Python lists which we are using for our array are actually themselves already lists. In fact, I think they're actually implemented as array lists. For the purpose of this demonstration, though, we're pretending that they're more like an array in C, in that they are fixed in size, though of course that's not the case with Python lists. So just be clear that you would never actually create this Python class, or even any implementation of an array list in Python, because it already has a built-in list class. What are called queues and stacks are like lists, but they are artificially constrained in that items can only be added to one particular end of the list, and also removed from only one particular end of the list. In a queue, items are appended on one end of the list and then removed from the other, whereas in a stack, the items are appended to one end of the list and then removed from that same end of the list. So as the name suggests, a queue is like a line of people, where people join the line at the end, but only leave the line from the front. And a stack, like the name implies, is like a stack of plates, where you only place plates one at a time on top of the stack, and you only remove plates by taking them off the top one by one. We've already discussed stacks in the context of the call stack. Each function call adds a new frame to the so-called top of the stack, and when the current function returns, the frame on top of the stack is removed. This pattern is also known as LIFO, last in, first out. The last thing added into the list is the first thing next removed. Likewise, queues are also known as FIFOs, first in, first out. The first person to join a line is going to be the first person through the line. Now, in both the case of queues and stacks, they can simply be implemented as just a regular list, but with slight modifications to the available methods, the available operations, such that there is no operation for, say, inserting an item in the middle of the list, or removing items from the middle of the list, or even reading the items in the middle of the list. To be a proper stack or queue, the only operation is to add an item and remove an item, one at a time, and only at the appropriate ends of the list. Now, you might be wondering if there's such a thing called a first in, first out, and a last in, first out. What about a last in, last out, and a first in, last out? Are there such things? Well, logically, a last in, last out would be the same thing as a first in, first out. The last person to join a line is going to be the last person through. Likewise, a LIFO, a last in, first out, is logically the same thing as a first in, last out. The first plate added to a stack is going to be on the bottom of the stack, and so it's going to be the last plate removed. Though LILO and FILO are logically equivalent to FIFO and LIFO respectively, you almost never hear those terms used. The proper terms are FIFO and LILO. Let's look now at how we might implement a stack using nodes, very much like a linked list. So we're creating a Python class called nodeStack, and in its constructor we're simply assigning to an attribute called top, initially the value none. Top is the attribute that keeps track of the node which is at the top of the stack, though at the start the stack is empty. And by convention, when you add something to a stack, that operation is called a push. So we have a push method which takes as argument an item, and we create a node for that item which is going to be the new top of the list. So in the case where the stack is empty, self.top is none, so the new node is pointing to none, which is actually the default value anyway, and then the new node is assigned to self.top, and now we have a stack with one item in it. If, however, there are already items in the stack, then self.top is not none, and we're creating a node which points to the old top, and then the new node is being assigned to self.top. It's becoming the new top. So understand that the structure of our stack is a chain of nodes, where the top node, the top of the stack, is the node at the start of the chain. And the chain of references go from the top to the next item, to the next item, to the next item, all the way to the end, the bottom of the stack. So be clear, this is sort of a reversal of how we did our linked list, where we were appending items onto the end of the chain. Here we're appending items onto the front of the chain. Now, the operation to remove and return the top item from a stack is traditionally called pop. So we have our pop method, and notice it takes no arguments because there's no question of what we're removing. We're always removing the top node. And first we're checking to see if there is a self.top node, and if there isn't, then we're going to raise an exception saying, hey, you can't pop because the stack is already empty. Otherwise, we simply take the top node and retrieve its value with getItem and return that, but before returning, we need to remove the top node from the stack by simply reassigning self.top to the node which the old top pointed to. So we invoke self.top.getOther to get that node. What's called a map, or sometimes a dictionary, or most generically called an associative array, whatever we call it, it's a collection of key-value pairs. The items are stored with no sense of logical order, rather values are stored and retrieved by their associated key, which must be unique in the collection amongst all the other keys. Perhaps the simplest way of implementing a map closely resembles a linked list, but rather than in each node storing just a single value, we store both a key and a value. The obvious downside of this implementation is the performance costs of the basic operations. Like, say, if we want to insert a key-value pair, well, first we have to actually look through the whole list to see if there's a node already with that key, because keys are supposed to be unique, so we can't just add a new key-value pair without checking first. In the special case where we want a map where the keys only need be integers in a limited range from 0 up to some number, we can much more efficiently implement the map using just an array. Here, for example, we can use a 5-element array for a map as long as we're happy with keys limited to the range of integers 0 to 4. We then store the values for each key in the slot associated with that key. So, for example, the value of key 2 is stored at index 2 of the array. Now, while a much more efficient implementation, it is much more constrained. Ideally, what we want is a map with the efficiency or near efficiency of this array implementation, yet which allows us to use any possible key. The solution to this problem is what's called a hash table, which is a map that uses a hash function to associate the key value pairs. What though is a hash function? Well, a hash function is a function which takes any input value and returns an output value, a hash, which is constrained to a smaller finite range. So, for example, a hash function might take in any integer as input, but then the output might be constrained to a finite range, like say 0 to 100. Now, because the set of possible inputs to a hash function is always larger than the possible set of outputs, inevitably multiple inputs will have to produce the same output, the same hash. When different inputs produce the same output, the same hash, that's called a hash collision. Perhaps the simplest case of a hash function is one that simply returns a modulus of the input. So here, for example, our hash function mod5hash takes an input value and then returns simply the modulus of that value by 5. So for the inputs 5, 102,135, -95, and 10, those all produce the hash 0. And then the inputs 21, -4, 6,781, those all produce the hash 1. 7, -303, 92, and 12, those all produce the hash 2, and so forth. And you see that there are actually only 5 different possible outputs, 0, 1, 2, 3, and 4. Though a very simple function, a simple modulus is generally a very appropriate hash function for a hash table, because given a set of random inputs to the function, the distribution of the outputs tends to be uniform. So say we started feeding random numbers to our mod5 hash function, the outputs we get would be quite evenly split between 0, 1, 2, 3, and 4. Each output would occur on average 20% of the time. Again, this is assuming totally random input. A downside of using a simple modulus is that it can only be applied to integer inputs. Ideally, we want a hash function which can take as input any kind of object. We could quite simply, though, modify our hash function to accept strings as input. All we need is some way of converting a string value into an integer value. Here we have a function string to int, which does just that. it takes an input string s, and then it loops over the individual characters of the string, gets the numeric character code value of each character, and adds that value to a sum, and in the end we return that sum. Note here that the ORD function is a built-in Python function which translates a single character string into the ordinal value, the numeric value of that character. In any case, once we have this string to int function, we can then, in our mod5 hash function, first test if the type of the value is a string, and if it is, then we first need to convert the input value to an integer using the string to int function, and then we can simply take the modulus of that value. So, for example, if we now pass in the string hello, all in lowercase, to mod5 hash, what we get back is the value 2. Now, if we want a truly generic hash function, the obvious thing to do is to create a hash function that works by processing the individual bytes that make up that object. One of the simplest such techniques is called Pearson Hashing, where we define a substitution table in which every possible byte value maps to a different byte value. So here, for example, we have the value 0 mapped to 72, 1 to 94, 2 to 8, 3 to 204, 4 to 238, 5 to 27, and so forth, with the rest of the values not shown. Just understand that if 0 maps to 72, then no other value should map to 72. In other words, no two keys in this table should map to the same value. Also understand that this table is meant to be random, and there's no standard table for Pearson hashing. It's up to you to create your own such table, and understand that this means that the very same object fed to two different Pearson hashing functions will probably produce a different hash. Only when two Pearson hashing algorithms use the same table do they produce all the same hashes. In any case, we initialize the hash we're going to return to 0, and then we loop through the bytes of our object, and for each byte, we do a bitwise OR of that byte with the current hash value to get an index into our table, and then we assign the value found at that index to hash. Once we've gone through every byte of our object, we then return the hash value, which will be a value between 0 and 255. Now, you might wonder why we have to loop through all the bytes. Why don't we say just use the first byte and call it good? Well, what we're looking for is a uniform distribution in the output of our hash function. And so, given two objects, which are very similar in their contents bit for bit, except maybe for 1 or 2 bits here and there, we want the output from the function to be very different. And if we just used the first byte, or the first 10 bytes or whatever, then the small differences between objects, which might be buried, say, in the middle of the object, or at the end, they wouldn't get reflected in our output. And then if we ended up feeding quite similar objects to our hashing function, we wouldn't get a uniform distribution. We would probably end up with hashes which are clustered. That is, we'd see the same few values over and over, or the same small range of values over and over, when what we want is a uniform distribution, even when our inputs might be quite similar. In any case, Pearson hashing is one simple way to get a hash out of any object. The version we showed here is notably limited in that the hash range is only from 0 to 255. Sometimes we want a much larger hash value range. And I should also mention that hashing objects simply by reading their bytes as input is problematic in some cases because objects very often are composed of one or more references, i.e. addresses. And the thing about addresses is that they tend to be kind of incidental. When you allocate an object in one run of a program, it's generally unlikely to be given the same address in any other run of the program. But even if addresses were consistent from one run of a program to the next, they're still not really the true content of the object. Like say in Python, when you have a list of numbers, those numbers are not stored directly in the list, they are stored via references. The list object itself in memory is just a series of addresses. So even if we have two identical lists with all the same number values, their hashes are likely to be different because they don't necessarily reference the same number objects. You very well might have two separate objects representing the same number, one referenced in one list and the other referenced in the other list. So even though the two lists appear identical, a hash of the bytes of these lists as they are stored in memory will probably come out different. Depending exactly why you are hashing, that very well could be undesirable behavior. Getting back to hash tables now, assuming that we do have a proper hashing function with nice uniform distribution, and say that the output of our hashing algorithm is constrained to the range of 0 to 4, we can now store any value in our hash table if instead of directly storing the values in our array, we add them to lists which themselves are stored in the array. So, for example, if you want to add an object which hashes to 2, you append it along with its key to the list in slot 2. We can't, of course, just store the values, we must store the keys, because it's the keys in the hash table which identify the items. And in fact, to make sure that a key remains unique, when we add an item, we have to first search the list and make sure that there is no such key already in the list. If there is, we don't add a new key value pair, we rather modify the value of the existing key value pair. Now the virtue here of this kind of implementation of a map over the implementation which is simply a single list is that here we have split that single list up into 5, and assuming that we don't happen to add keys that all hash to the same list, the distribution of items among the 5 lists should be on average even. So when it comes time to retrieve an item from the hash table, we first hash the key we're searching for to determine which list to look in, and then we can search that shorter list rather than having to search a much longer list. In this example, we're only hashing to 5 different lists, but more commonly in practice, hash tables can be much larger. They can have 100 slots or 1,000 slots, each with its own list. Generally, the larger the array of lists, the fewer items you'll tend to have in each list, and so fewer items to search through when we add or set or retrieve a key value pair. This technique of using a list in each slot is called chaining. An alternative strategy is called open addressing. In open addressing, we don't add extra lists into the mix, we just store key value pairs directly in the array, but in the event of a hash collision, where we want to store 2 keys in the same slot because they produce the same hash, we simply look for the next available slot and store the key value pair there. So here, for example, say we have a key value pair already stored at slot 323 because it's key hashed to 323, and say that we get a hash collision. We have another key value pair we want to add to the table whose key also hashes to 323, yet which is actually a different key. We can't store it in slot 323, so we search for simply the next available slot, which in this case is 325, and we store it there. So when it comes time to retrieve a value from the table, we look first in the slot to which the key hashes, and if a different key is already in that slot, then we have to search through the rest of the table to see if the key is found elsewhere. Now you may be wondering what happens when this table gets full. Unlike in our chaining example where we have lists which can presumably grow as large as we need, in this arrangement we have a limited number of slots because the array is fixed in size. Well, in the event that we run out of free slots, the solution is to resize the hash table, which means to create a new, larger hash table and simply copy all the key value pairs from the old one into the new one. Obviously, this is not a desirable thing to do on a regular basis because it's very expensive. Also note that in the new table, because the array of slots is larger, the hashing algorithm has to be tweaked to produce hashes of a larger range. Like say, if our original table had 100 slots, and so we used a hashing algorithm that spit out values from 0 to 99, if our new table has 1,000 slots, then it needs to spit out values from 0 to 999. So this tweak to the hashing algorithm means that the key value pairs as stored in the original table are not necessarily stored in the same slot in the new table. When we resize the table, items get moved around. Lastly, another possible variant of chaining is to use a second level of hash tables rather than lists. These hash tables themselves may use chaining with lists, or maybe even another layer of hash tables, or they may just use open addressing. Conceivably, you could have many levels of hash tables within hash tables within hash tables. The choice ultimately comes down to what's most efficient given your storage needs. Very importantly though, these hash tables should not use the same hashing function as your top-level table. If they did, then every value inserted into these tables would hash to the same value. They'd all cluster into one slot, which really defeats the purpose of hash tables. So, for example, if you insert a key value pair where the key hashes to 2, and then when we insert into the hash table in slot 2, if the same hashing function is used, then every item that goes into slot 2 of our top-level table is going to end up in slot 2 of the hash table in that slot. So the nested hash table should use a different hashing function so that that doesn't happen. Again, we want a uniform distribution in these second level hash tables, just like we want a uniform distribution in our top level hash table. And this principle applies all the way down. If we have 3 levels of hash table, if within our second level of hash tables we have a third level of hash tables, well, those third level of hash tables should use yet a different hashing function. Otherwise, again, everything would cluster in just one slot. What we call a graph is a set of nodes, in this context also called vertices, and in this set, any one node can be associated with any other node via a connection called an edge. So in this diagram, for example, we have a vertex with the value 5, which is connected to the vertex 1, 2, and 4. Now, what these connections signify is up for grabs. Depending upon the context, it may mean different things. And in some graphs, we give these connections values called a weight. And in some cases, edges are directed, meaning that, say, the connection between 5 and 2 is asymmetrical. Just like, say, in the relationship between a parent and child, it matters which is the parent and which is the child. The same is true with vertices connected by a directed edge. What the nature of that asymmetry is up for grabs. It can differ from one graph to the next. Like, for example, imagine a graph in which the vertices represent locations, physical locations, and if the edges have both weight and direction, the weight might signify the distance between those locations, those vertices, and the direction might signify that travel between those two locations can only go in that one direction rather than the other. Such a graph representing locations, travel distances, and travel directions, a graph like that is what we would use if we wanted to calculate optimum travel routes. Now, one thing to be clear about is that a diagram of a graph is not necessarily meant to accurately reflect the respective locations of these vertices. In fact, in many graphs, vertices don't represent locations in two-dimensional space. All that really matters is the set of vertices and the edges between them. In this diagram here, for example, if we were to take that vertex 6 and draw it instead on the right side of the graph, well, that doesn't change anything as long as we still see an edge connecting 6 and 4. So again, in these diagrams, the depicted relative locations of these vertices is just a convenient fiction that makes the graph easy to look at. As I mentioned, graphs are used for many different purposes, such as the example I gave of computing optimum routes. As for the implementation of a graph, its storage in memory, there are several different techniques, one of which is to keep a list containing just the vertices and another list of all the edges. Alternately, especially in the case where you want directed edges, you could create a node type that contains not just one reference to another node, but potentially many, and you could then represent a graph as a set of these nodes, with the references from the nodes to other nodes representing the edges. A very common special case of a graph is called a tree. A tree is a graph in which any 2 points are connected just by one path. That is, to traverse from any one vertex to any other, you could only get there by following one set of edges. So here, for example, to get from vertex 1 to vertex 3, the only possible way is to go from 1 to 4 and then 4 to 3. There's no other route. The most common kind of tree we deal with is called a rooted tree, in which one node is designated as the root and all the edges point away, or in some cases towards, that root. So here, for example, the vertex with the value 2 is our root node, and all the edges are pointing away from that root node. In the terminology of a rooted tree, we also have what are called leaf nodes, which are nodes other than the root node, which only have one edge. It's possible to have a rooted tree in which the root node also has only one edge, but the root node is never considered itself to be a leaf node. Rooted trees are obviously very useful because lots of data is by its nature hierarchical. For example, the file directory structure is a hierarchy. It's a rooted tree, hence the term root directory. Like with the more general graph, there's many ways we could implement a tree. Again, the most obvious being to use 2 lists, one to store the edges and one to store the vertices, or we could use a system of nodes. There are many variations, but we won't get into them here.